So we started chapter 16, and I want to do this will work. Okay. Well, let's try this. Okay, so a little bit more for this section, and then we're going to skip 16.2 and start 16.3. The sample space we call S, capital S. Okay, it's kind of like the universal set, but when you talk about an experiment, it's more specific, and it's S as your universal set with this name, sample space. All right, any subsets of the sample space are called events. And we like to do some capital letter like E or capital A. I feel like a small picture would help, but we're going to do a lot of examples. So your set of all outcomes, like this. And your subset E. Just put like 1, 2, 3. Okay, in this case, set S.
What did you write on the outside of E?
I put 1, 2, 3. So like S contains 1, 2, 3. And E contains 1. All right. E is called a simple event. I don't know if it'll come up very much, but it is one of the specific types of events. So a simple event is an event that contains one element.
Does that say simple event?
Yeah.
Kind of really.
We'll do a few. Hang on here. I'm gonna get better setup. Okay, that's better. All right, let's do another example. So we'll have S be the set that contains So this was the sample space for flipping 2 coins. It was heads, tails. Well, let's do heads, 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 tails, tails, heads, tails, tails. Okay. And E is the set that contains heads, heads, getting heads on the first flip and then heads on the second flip. But that is one outcome. So that is a simple event.
So would that say ask the we're all ask heads, tails, heads, or tails, tails, and then if it say heads is the correct answer, then we would term it a simple.
It broke up a little bit, but basically I think I'll try to do my best to explain what the experiment is and what each of these events are. I'm just kind of like jumping through the explanation right now. I hope that helps. Well, there's 2 more to cover. An impossible event. I think that is the empty set is an event, and it is called the impossible event. So I can write, can't really do an example. Okay, the empty set, which is like empty brackets, which works. Or you can do this symbol. I think it looks a little better. Okay, it is a subset of every set, including S, and it's called the impossible event. Last one is that S is a subset of itself, and it is called the certain event. T-A-I-N. Yeah. Okay, let's do some examples. So S is a set that contains 1, 2, 3, 4. Okay. let's talk about two subsets. First one we'll call A. It's a set that contains 4. And B will be a set that contains 2, 4. I think all we want to do right now is draw what's happening. The sample space contains all of the elements. A and B share the number 4, so we do want an overlapping part with 4 in the middle. A and B. And then 2 is in B, but not A. It's over here. And you have 1 and 3. I guess all I can say is that A is a simple event, but I don't know if I'm going to actually ask any questions about that on homework or tests. It's just an interesting part of the chapter. Again, S is a certain event. This is a simple event, and the empty set, which we can't really draw, was called the impossible event. All right, so 16.2 is about counting. Counting is kind of, it is useful for finding probabilities if we actually want to do experiments where we do a lot of counting and finding out all the possible ways something can occur. I'm going to keep our experiments kind of small, where we can actually just count them ourselves. And we're going to jump to 16.3 and start doing probability. Okay, so first we'll write out what it means, and then a little bit of notation, and then a formula.
What did you say was our standing on 6.2? That we're just kind of glazing by it, or
We're not
it's
going to
simple
use,
enough we can, oh, not can even do.
yeah, we won't use 16.2.
Okay.
Yeah, I've taught it before, but then after teaching it, we never actually used it. So we're going to just pass on through. Yeah. So probability is the measure of likelihood that an event will occur from an experiment. Measure of, what I wrote down actually is chance, which is the same. The measure of the chance that the event will occur. As the result of an experiment, but the whole focus is on experiments. And probability will have a notation of capital P for probability of an event E. So E Okay, so I kind of skipped a part where what we have is a function that measures the chance that your event will occur, and it assigns to each event some number between 0 and 1. So this is actually a function here, capital P, and it takes your event to some number between like 0% and 100%. And here's the formula. P of E, probability of E, is equal to the number of outcomes in E, and then divide by the number of outcomes in S. So divide by the total. It looks similar to relative frequency. Let's see. I think it is actually like the same idea. Let's do some examples. Okay. S is the set. S will be the set that contains 1 through 7. Okay. E contains 2, 4. The other event is F, and it contains 1, 2, 3. I think it helps to draw a picture. So the sample space will contain all of the elements. E and F share the number 2, so they do overlap. We need 4 in this set and 3 over here along with 1. And then get the rest of your elements. We've got 1, 2, 3, 4, 5, 6, 7. Let's find the probability of E. So what we could write is the probability of the set that contains 2 and 4. We'll do that in the future. We're going to put the number of outcomes in E over the number of outcomes in S. Two out of 7. Let's get the probability of F. Okay, we'll do that now. Probability of the set that contains 1, 2, 3. is 3 out of 7 total. I think that's good enough. Let's do probability axioms. So there's 3 of them. All right, the first one, the probability of the empty set is 0. The second one, the probability of the sample space is 1. The third one, a little bit. For any event E, the probability of E is between 0 and 1. We're going to do 0 will be less than or equal to probability for E less than or equal to 1. So probabilities are always between 0% or 100%. Anything else to say? Okay, one more thing. And then a bunch of examples. There's one more event, an unusual event is any event that has a probability that is less than 5%. Let me see. Is it an event is usually if it has a low probability, usually less than 5%. That has a probability. Okay, so for most classes, it's been, if it's anything, I guess maybe less than or equal to 5% probability, we're going to call it an unusual event. All right, more examples. S is the set that contains A, B, C, D, E, F. We will find probabilities for, let's see, A equal to BC, the set that contains little b. And let's let B be the set that contains A, B, C, D. Let's draw the picture first. S. I need A and B to overlap. They have got these two elements in common. All right, this needs A and D, A, B, C, D, E, F, somewhere over here.
The A and the D would be in the B and B, professor.
Thank you. Yep. Cool. Thank you for finding mistakes. A, B, over here. Let's do part B is to get the probability of A. The number of outcomes in A, there are two elements in there. How many total? 1, 2, 3, 4, 5, 6 elements total. Let's get the probability of B. Probability of B is take the number of elements in B, 1, 2, 3, 4, and out of 6 in the whole space. I want to find, in part D, find the set A complement. A complement is everything except for A, so we need A, B, E, F. Part E finds the probability of A complement. Do this over here. So there are 1, 2, 3, 4 elements in that set. And then divide by this total in the whole space. This 1, 2, 3, 4, 5, 6, 6. Okay. Let's keep going. I want to talk about disjoint sets and then the complement rule. I think that this semester I'll mostly use the word disjoint, but disjoint and mutually exclusive mean the same thing. So two events two events A and B. Are disjoint. And to me, it seems to make most sense if we just write out what it means, but there's also like a mathematical, we can do it with symbols too. Okay, so what it means in words is if they share no common outcomes. So in symbols, it means that A and the intersection of A and B is empty. There's nothing in that shared part. So you could write disjoint, A and B are disjoint.
Is that like if the S equals like 1, 2, 3, 4, 5, 6, 7, and A has 1 and 2, and B has 6 and 7, they would be disjoint because they don't share anything?
Yeah, exactly. It's probably like perfect example. But we'll just do a picture. Yeah, we could do this kind of space. S, A. Doesn't need to have anything with B. We put like 1, 2, 3, 4, 5, 6, 7. Yeah, those would be disjoint sets. And let's see. I made another one with a sample space that contains W, X, Y, Z. Okay, our events are going to be A equal to WX. And B contains Z. So first we're going to ask, well, we will draw, let's first draw a Venn diagram. And then we're going to ask, are the sets disjoint? Okay, I mean, you can have them overlap. It's just going to have an empty part here. With A containing WX, B contains Z, and the space has WX, Y, Z. Okay, are A and B disjoint? Like explain. So what you could say is A intersect B equals the empty set, which means they are disjoint. Or you can just write everything out. Yes. A and B are disjoint. So you don't have to write both. You can just explain once as a sentence, or you could have responded as, yes, A intersect B equals the empty set. So I'll just kind of separate that. But you don't have to say both. Just, I've seen it in the past. It's a bit too much. Pick one or the other. So another way to say all of this is, yes, A intersect B equals the empty set. Okay. We're going to keep using this problem. Let's get the probability of A. Number of outcomes in A divided by the total number of outcomes in S. You've got 2 elements in A and 4 elements total. Probability of B. Number of elements in B, which is just 1, out of 4 total in a space. The last thing to cover today, and then as many examples as we can get through, is called the complement rule. So we'll introduce some event. We'll call it, let's call it A. Let A be an event. The probability of A complement is 1 minus the probability of A. Complement rule, S is going to be the set that contains 1, 2, 3, 4, 5. A is the set that contains 1, 4. Find the probability of A. So probability of A is the number of elements in A and divide by the number of elements in S. There's 2 elements in A, 5 total in S. Now find the probability of A complement. Part B. We'll use the rule. The rule is to take 1 and subtract the probability of A. Okay, 1, subtract 2/5. I've got 5/5. Subtract 2/5. 3/5. Alright. I made a new space. Let's go ahead. Okay. S is the set that contains 1 through 9. Oops. Okay. All right. A is the set. Well, actually, capital E is the set that contains 1, 2, 4, 7. F contains 3, 8. 3 and 8. First part is to draw a Venn diagram. This could be better. All right. Cool. All right, S has subsets E and F. We'll just have them overlap in case they share common elements, but it doesn't look like it's going to happen. Okay. 1, 2, 4, 7. 3, 8. 1, 2, 3, 4, 5. 6, 7, 8, 9. R, E, and F disjoint. Yes, they don't share any common elements, or you could say the intersection is empty. What next? I did find the probability of E. here. A contains 1, 2, 3, 4 elements, and there are 9 total. All right, last part. In part D, finds the probability of E complement. Okay, take 1 and subtract probability of E. Minus 4/9 and get 5/9. Okay, next example. S equal the set that contains. It's going to check that we didn't already do this problem before. Okay, this one is A, B, C, D, E, F, G. Let's call it A contains A, C, D, E, G. B contains C, D, G, B. Start with a Venn diagram. Okay. Okay. Subsets A and B and S. A with, well, actually, let's go in here where they do share elements now. In the common space is C, D, G. Then we've got A, C, D, E, G. C, D, G, B, A, B, C, D, E, F, G. Okay. Oh, oops, I put D twice is in that. It's already been used. And that's the correct picture. Are A and B disjoint sets? No. They share common elements. And if you want to list the elements, you can, but you don't have to. You can just say no. Okay. Another way to say this, and you don't have to say both of them, you can say this, or you can say it with like more math symbols, you can say no. And I mean, if you put an answer down and it's just your way of explaining what's going on, I will try to understand, as long as, we're explaining the right thing. So no, A intersect B is not the empty set. So if it equals the empty set, they are disjoint. If it does not equal the empty set, they are not disjoint. Let's get the probability of A. Okay. I'm just going to look at my sets. In the set A, we had 1, 2, 3, 4, 5 elements. And then count how many elements are in S, which is 1, 2, 3, 4, 5, 6, 7 total. Find the probability of A complement. And you could find the set A complement and then get its probability, or use the rule. So using the rule, we'll take 1 and subtract the probability for A. And 1 subtract 5/7. I got 2/7. I think we have, so we're going to change it up a little bit. We have some time to do a few more examples and then save the rest for later. So in this situation, you're told what the probability for an event is. We'll start here. Let's see, 5, 7. Let's try this here. Okay, and then it's just asking to find the probability of the complement of E. Probability of E complement is 1 minus probability for E. All right, take 1, subtract what they gave you, 0.57. 3 more would get you to 60. So we 4, 3. We can always just check on a calculator. One, take away 0.57. And we got a 0.43. This time. And this one's really just for fun. I wouldn't put this on your assignments. So the probability that it will rain tomorrow is 0.87. Find the probability that it will not rain tomorrow. So the event is if it's going to rain. And we want the probability, P for probability, of, we'll just put rain. Actually, we want that it will not rain. So probability of no rain. Okay, take 1, subtract the probability that it will rain. And get 1 minus 0, 0.87. It would be another 3. It should be 0.13. Again, you can just double check. Okay, just check it. Let's do one more. Okay, this time, a bag contains 100 marbles. There are 30 red, 45 yellow, and 25 purple marbles. Okay, 45 yellow. 30 red, 25 purple. Part A. Find the probability that a randomly selected marble is red. Okay, so getting a red, we're going to just go probability of red. Marble has 30 possibilities for that color out of 100 total possible chances. Let's do the probability for purple. So part B, find the probability that a randomly selected marble is purple. We will write P for probability of purple. Is the number of chances for getting a purple marble out of 100 total. That was 25 purple, 100, okay, 0.25. And the very last one, part C. Find the probability that a randomly selected marble is not purple. And we'll do it this way. Probability of not purple will be 1 and subtract the probability for purple. Okay, 1 subtract 25 out of 100 to be 75 out of 100. All right.
You could also do it I mean, it's just in the terms of which way you want to solve it, but you could also just do the add up what isn't purple, right? Okay.
That would be good. Yeah. We're going to do more examples next time, so we're just going to end it there today. Okay, thank you, everybody.